All right, let's start. Yesterday, we talked about the intuition behind dynamic programming. By using the additive property, we looked at the three options, three choices we had for the first position of the alignment. And if some oracle or an algorithm gives us the optimal alignment for the rest of the sequences, we basically combine these two scores, we add these two scores and see what is the overall result of choosing either of these three options. And this is how we can find the optimal alignment. We can do the same thing using the sequences using the end of the sequence. It's like this. If somebody gives you, again, two sequences, okay, the analysis we have done right here, we can do the exact same thing for the end of the sequences, right? I mean, this asks for what is the first position of the alignment. We have three choices. And similarly, we have three choices for the end of the alignment, which could be, so let's try to do the same thing for the same sequences, CA-CGA and CGA. Okay? For the end sequences, we have, again, three options. Let me just erase this one. Our first option being alignment of A with an A. This is our first option. Our second option is alignment of A against a gap and alignment of a gap against the second A. Okay? So considering the end characters of these sequences, we have just these three options. Any alignment you have, okay, out of all these exponential number of alignments, okay, you may have, by using the gaps, you can have an enormous number of alignments, even for these small sequences. Okay, but the last position should be one of these three. Can you think of any other alignment? And no, I mean this is the only way you can do. So if the alignment ends look like this, then we can ask, what we are going to do is, if the alignment end is going to be one of these ends, then which one gives us the best overall alignment? So we do the same thing here. If the alignment for each of these options, okay, option 1, option 2, and option 3, we are going to need an algorithm to give us the alignment, the optimal alignment for the rest of the sequences, for the beginning part. So for the first option, if I have chosen to align A with an A, and if I have a technique that is going to give me the best way to align CA-CG with CGA, okay, if you know the optimal way of aligning these first parts, CG. If A is aligned with A, I'm left with CG for the second sequence. Okay? So if I have chosen this as the last position of the alignment, which means that somehow the first part is aligned. I don't know the answer to that yet. Okay? But this is what I've chosen for the last part. I'm sure for this. And if using the same algorithm, using a similar algorithm which finds the optimal sequence alignment, if you can find this part, then the overall score of the alignment would be the score of this optimal alignment plus a match score. Okay, score of this one, S1 and S2. So the overall alignment would be S1 plus S2. So we can do the exact same analysis for these two. And at the end, what do we get? We get this. The optimal alignment, which contains all of the sequences. By looking at these three options, we can basically judge which of these three options gives us the best overall optimal alignment. We are going to compare each of these S1, S2s for all these three options, and at the end, for the complete sequences, we get which option actually produces the best alignment. So the dynamic programming idea is based on this reverse idea. By looking at the end of the sequences, we are going to grow, starting from an initial alignment, we are going to grow this alignment until we get to the end of the sequences. This is, the whole idea is based on these three options. Okay, so everybody understand this part? Or anything unclear? Okay, so yes. So if we match the A's, if you look at the sequences, we are talking about the A's at the end of the sequences. Okay, if we match the sequences, the A's, the first part of the sequences cannot be to the right of these A's. Okay, because they're at the end. We need to preserve the sequence order. If we have matched these A's, the first prefix, these sequences should be matched, both of them should be matched to the left of the respective A's. They cannot be to the right. But what you're asking is, maybe you're asking the CG. Why did you align? I didn't show the alignment here. Okay, I just said that the task is, if you chose to align A with an A, now the task is to align CA-CG with CG. Okay, I didn't give you the alignment. This alignment could be like this. Okay, C, C, gap, gap, G, or it could be gap, gap, CG. Okay. So I didn't give you there are many choices. The thing is, we do not need to know what this alignment is right now. We are going to use the solution to this, but the most important property of a recursive solution is that you just assume that there is an algorithm that gives you this smaller problem, solution to this smaller problem. And we are going to get also, to solve this problem, to solve the CA-CG problem, we can do the exact same thing, okay? If we are going to align these two sequences, the last position of the alignment can either be GG, G-gap, or gap-G. So we are we are shortening the alignment at every recursive call. At the end, we are going to come up with a base case in which we are not left off any letters in these sequences, where we have the score of 0, which is your leftmost top corner of your table. So this is how the dynamic programming works, by dividing by solving the problem by dividing it into smaller pieces, by asking the same question for a smaller set of sequences. Any other questions? So here's an example which just shows a table partially completed. The first, as you can see, we have an additional column, additional row and a column, which we also label them as gaps, which represents the alignment of initial gaps. We can, for example, initially, if we do this alignment CA-CG with CGA, we can have a terminal. These are called terminal alignments, terminal gaps. Gaps which occur at the end of the sequence are called terminal gaps. And these terminal gaps, which are the first CA of the first sequence is aligned with these two terminal gaps. Such gaps can only be modeled by using a gap row and a gap column. Okay, so meaning, for example, a -16 here means that the first two PA is aligned with gaps. So we have consumed the P and A amino acids of this sequence, and we haven't aligned any of these amino acids yet. So the first P going this path means that, okay, if I start from this 0, and if I choose to go this path, it means that I'm aligning this PAW against gaps. Okay? And this, do not forget this. Any cell here, okay, any cell here, Fij, here I and j can both be zeros, or they can be any number between n and m, okay, between 0 and n, and 0 and n, so I is equal to 0, n, and this is 0, n. If my first sequence is of length n and the second sequence is of length m, Fij denotes the optimal, so the entry in that table is a number, which denotes the optimal score of aligning the first I characters of the first sequence with the first j characters of the second sequence. Okay? This is what you need to understand the meaning of an entry in this table. It shows the optimal score of aligning, I repeat the same thing, the optimal score of aligning the first I characters of the first sequence with the first j characters of the sequence, second sequence. Okay? It shows the score of the optimal alignment. So, here, if you look at this cell, which is F03, here it's minus 24. Okay? So let's look at F03. What does this mean? The first 0 characters of the first sequence align with the first 3 characters of the second sequence. This is an alignment problem, but it's a trivial alignment because the first 0 characters means that you do not align any amino acids. You have one option. Actually, the first 0 characters align with the first 3 characters. You have only one alignment option, which is gap, 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 and gap, 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 and PAW. Okay? So, and that's the only thing we have. That's the only alignment option we have for 03 because you're not allowed to use any amino acids from the first sequence, which is this HEAGAW. Okay? So, therefore, we have only one alignment, which is this, PAW and gap, 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 and the score of that is going to be minus 24. If your gap penalty is linear and minus 8, this optimal score of this alignment, the first 0 characters align with the first 3 characters, the optimal score is minus 24. Actually, that's the only score that you can get. The worst and the best score for that alignment is 24. That's because they're only option of alignment. But for the other alignments, you are going to have multiple options. Let's look at this entry, which is minus 2. What does it, so we are asking now, what is F11? Okay, F11 is not given yet. I mean, it's not initialized, we need to fill it. So F11, it's determined to be minus 2, but how do we determine it? And here, F1, so F11 asks this. What is the optimal way of aligning the first 2 characters, P and H? Okay, what is the optimal way of aligning the first 2 characters? It's asking PH and the rest of the sequences, we do not care about them. So F11 asks, what is the optimal score of aligning P with an H? How many options we have? 3 options. I mean, we have what kind of alignments? We can have this alignment, we can have this alignment, or, sorry, this one is 1, okay. We can have PH directly aligned with each other, or we can have P, sorry. So this is, okay, these are different alignments. This is the first alignment, this is the second alignment, this is the third alignment, which is going to be gap H and P gap, okay? Or we can also have a fourth alignment actually, right? We can have an alignment like that. No, we have, no. right? These are the 3 alignments we can have. So, and these 3 alignments, okay. So, for the first position, we have these 3 cases. I'm not the first. To find this, F11, I have, the first alignment can be like this. If the alignment, the second alignment, if these are aligned with each other, what we look at is that we look at the rest of the beginning of the sequence, which is both null characters, okay? I have no characters if I aligned these 2 pH, meaning that the previous, so it's like this. The best score of aligning F11 is equal to F00, the best way of aligning F00 plus the score of matching the first characters, the first character of the A sequence and the first character of the B sequence. Okay? So here, if you have chosen this alignment, the F11 is going to be equal to either of these, okay? Which one has the better score? But now, how can we compute their overall scores? What is the score of this? What is the score of this? What is the score of this? Now, the score of this is easy. I mean, if you just align it with P and H, but we basically need to go to, if you align P and H, what are you left in terms of sequence? You are left with nothing. There are empty characters at the beginning of the sequence. So this is our initial position actually. And the score of this alignment is alignment of P with an H, which is -2, given as score of HP from some Blossom or PAM matrix. We need to have a scoring matrix to give us what is the score of aligning H with a P, and it's given to us as -2. Okay, so the score of this alignment is -2. What about these 2 alignments? We need to also look at them in order to find out F11. Do not forget that F11 still shows the best way of aligning the first characters. And we need to also look at these other options. And this one, if you look at the last position of this alignment, it is H aligned with a gap. So H aligned with a gap, if this is, we are looking at the last position here. If H is aligned with a gap, the first position can only be P aligned with a gap. So here it denotes this, so H, it denotes coming from this direction, okay? So from P aligned with a gap, what is the best score of P aligned with a gap? -8, okay? P aligned with a gap is actually, so we are going to be looking at the maximum of this or F01 plus the gap penalty, or F10 plus the gap penalty. So these 2 alignments, these 2 other options, we are going to add a gap penalty here, but we need to also consider if this is my last position. In these 2 choices, we have 2 different last positions, and each of them is going to indicate a previous alignment score. So it's going to be, we are going to have -8 from here, -8 from here. So in other words, you can consider filling this table entry like this. We are going to look at our 3 neighbors, 3 previous neighbors. To fill in this -2 entry, we have 3 choices. One of them is coming from this left cell. The other is coming from the top cell, and the third one is coming from this diagonal cell. Okay, this -2 is determined by looking at these 3 neighbor cells. And coming from the left or coming from the top means that we put a gap. So here, coming from the left means that H is aligned against the gap. Okay, we didn't consume anything from this PAW sequence. we are coming from the left cell, it means that you put a gap against this H amino acid. And coming from the top means that you do not consume anything here, you put a gap against this P. Now, if you come from this cell, so what is this? This -8 was H aligned with a gap. So, if you come from this cell to this cell, what you did was, you align P with a gap now. So, it's like our alignment becomes this. So, okay, so the path, which is this, consider this path. Okay, now, from 0, 0 to left and from 8 to down. Okay, if we take this path, which is of 2 hops long, so we take we walk from here to -8, from -8 to here, it denotes this alignment. Okay, the third option. And the score of that alignment is actually, what is the score of this alignment? -16, right? I mean, just consider, look at this alignment. It's -16. So why don't we have -16 at that cell? Because -2 is a better score. So we are not keeping all the scores in the cells. We are just keeping track of the best scores. For F11, I don't need these words alignments. Because in both of these sequences, the first characters are consumed. And the best alignment that consumes the first 2 characters is this, aligning P with an H. I do not need these 2 other alignments because they are useless. They do not give me a good alignment. So at each step, each step, we are keeping track of the best alignment. So this is how it goes. So since you know how to find out this -2 is found out by taking this path, this diagonal path, 0 plus -2 gives us -2. We do the same thing, so the next cell we can fill in. What is it? Which cell can we fill in next? So you need, in order to fill in the next cell, you need 3 neighbors. You can either fill in this cell, okay, which is 2, 1, okay. You can either fill cell F21 or you can fill F12, okay. You can the next step is going to be finding the value of this cell or this cell. So you can there's no unique solution. You can either fill this table column by column like this, or you can fill this table, which is the more conventional way of doing so, row by row. I mean, you can find out the value here. What do you need to find the value under this cursor right now? What do you need? You need the score of aligning P with an E, okay? First of all, here, to find the score here, if you are going to take the diagonal path, it means that P is matched with E. So all the diagonal, anytime you're coming from the diagonal neighbor, looking at those 3 neighbors, if you're coming from the diagonal neighbor, it means that you have matched P with E. So you need to know what is the score of matching P with E, or what is the penalty of matching it. So you need to, this is where you look at your BLOSSOM or PAM matrix to look up your score. And if you take this path from the top or this path from the left, it means that you need to know the gap penalty. So any path from top or left is you need to add the gap penalty. And one common mistake when I gave some either in midterm exam or maybe I gave also some written homeworks about this. It's a very common mistake, and even when the users are taking this path, they may make use of the score of matching P with an E, okay, which is an error. If you're taking, for example, oh, this is good, this is -2. If P and E, for example, assume that PE, the score of matching P with an E, is 4, okay? Assume that matching P with an E is 4, which may be incorrect, okay? I just made this number up. Assume that the score of matching P with an E is 4. Now, oh, okay, minus 2 plus 4 plus 2, that's a good score. Minus 8 plus 4, that's minus 4, that's not very good. So this is wrong. You cannot do it like this. You cannot use this score of 4 to come from, you cannot add that score to this minus 2. Because it means that P is already matched with H, okay? If, I mean, what does this minus 2 means? P is, I mean, that path was P, we aligned P with H. Can you align the same amino acid with E now? No, you cannot. You have a one-to-one match. So taking from this left path means that you are matching E against the gap. Okay, so that you need to do minus 2 plus minus 8, which is going to give you minus 10. And here, minus 8 plus 4 is going to be minus 4. It's going to be a better score than minus 10. So we are going to fill in this table. And not every cell is going, so at the end, what we are going to come up with, I mean, some intermediate cells may not be used in the optimal alignment. Okay, so it's because at the end, we are going to find out the value of F and M, okay? The final, after the table filling is complete, we are interested in this, okay? That's what we are interested in, F and M. What is the optimal way of aligning these complete sequences? And optimal score of alignment is going to be at this table entry, F and M. And we will just discard the other table entries. But some table entries may still be useful. Now, the question is, I have given you the score. The best way of aligning these two sequences is, I mean, not the best way, the best score of alignment of these two sequences is, for example, 20. Okay? Now, what is the alignment? We need to also find what the alignment is, right? You're just not interested in the score as a biologist. So the score maybe, okay, the score is 20. Now, can you give me the alignment? Which letter is aligned with which letter? If I give you a table like this, okay, that was your hint. Okay, so do I have it? Yeah, if I give you a table like this, okay, the final entry is 10. The optimal way of aligning is 10. Now, what is the alignment? How can we find the alignment? Yes? Yeah, we need to trace back from this cell. We need to first ask this. Okay, this 10. From which of these neighboring cells we obtain this 10? That's very important. Each of these cells here, okay, any intermediate cell here, its value is computed by using one of the three neighboring cells. And this shows it's like the story of Hansel and Gretel. I mean, you are just breadcrumbs. You put. Where did I come from? Okay, this is. I got this 10, but where did this 10 come from? It came from one of these three neighboring cells. So you need to do a trace back and find out your path from here all the way to the beginning of the sequences. So this path is going to give you the alignment itself. And this is the path to the optimal score. As you can see, there are some intermediate numbers here, like this minus 16 here, which is not visited at all by the optimal alignment. But we need this number. Maybe we may not know, maybe from this up to this point, if you align these the first three characters of this sequence with the first 5 characters of this sequence, maybe after that point you may have a very good match which is going to have a better score than 2. Just to see that, we need to explore these possible paths. But filling this table takes only n times n operations. Okay, n times m times some constant operations. So it's polynomial number of operations. Compare it to the exponential number of possible paths you could have drawn in this matrix. Okay, you get a means that dynamic programming solution is a good solution. I mean, you can do it in polynomial time without actually exploring all the possible paths. You're just, because here we are keeping track of the best path for every subsequence. We don't need all the possible paths. We just need to keep track of the best path up to that point. This is what we do. And this is this equation, this right here, is the heart of this dynamic programming solution. It just shows you how to fill in the table entry ij. Okay? If you look at this equation, it says that the value in ij, you need to look at the values in these three neighbors. What is fi minus 1, j minus 1? It's your diagonal neighbor. Fi minus 1, j, it's your top neighbor. And Fij minus 1 is your left neighbor. Okay? By looking at these three neighbors, you add the gap penalty to your to the score in your top neighbor and left neighbor and top neighbor, and you add the score of matching these I and j characters to your diagonal neighbor. So that's it. It becomes the rest is very simple by using the simple rule. By looking at you are going to compare these three numbers and choose the one which gives you the maximum score. Okay? Now, questions. What if two of them, or all three of them, results in the same score? What does it mean? Which one are you going to choose? Yeah, any one of them. What does it mean semantically?
There are multiple methods.
Yeah, there are multiple optimal solutions. There may be more than one way to obtain the same score of best alignments. Either, for example, this maybe this CACG. Look at this. If we use linear gap penalty, so this was G. So CACGA aligned with CGA. If we use linear gap penalty, and our max score is, for example, max score is 2, gap penalty is -1. So the score of this is 6 minus 2, 4. Okay, the score of this alignment. What about the score of this alignment? It's also 4, right? And they score exactly the same. So there may be sometimes multiple paths, multiple alignments, which will give you the same best score. So, this is sometimes we may, when we are tracing back by looking, we may have multiple paths to follow, and this is perfectly okay. You just report one of the alignments to the user, or you may also report information about how many different alignments exist that are all optimal. So if we continue filling in this table, we can either, as I said, go column by. We have all the information. If we go from left to right, we can fill in this row by going from left to right. We can fill in the first row, then we can fill in the second row, and we can go like this. Let's look at this. Now, what are we given here? The score of aligning E with a P, EA, and HA. So, okay, so the score of aligning E with a P is 0. Therefore, we can take this path to still keep at -8. Okay, to fill in this table entry, -8, I have used the score of aligning E with a P is 0. And also, the score of aligning E with an A is -1. So to fill in this table entry, coming from -2, we can get -3. Coming from top or left, we are going to get -18 or -16, which are both worse than this -3. So we choose this one. Okay. So HA is used here to align. Since its score is -2, again, we can come from the diagonal. Sometimes, in this example, it seems that all these table entries, beneficial to come from the diagonal always, but you are going to see sometimes putting gaps gives us better scores. Okay, and like this, for example. From here, we have a score of -4 at the left of this cell. Just look at this cell entry here. We have -28, okay? And this -28, even if the matching of G with an H is, for example, 10, we can, it means that this path was not very good. I mean, this diagonal ended at a bad score. Even if you have a good diagonal match, like GH score of 10, it will get you -18. However, there was a better path that ended at this cell, and you can have a gap of -8. You will have -12, but it's still better than -18. Okay, so sometimes using following a gap is better. And if you look at this final score is 2, and it is found by at each step, we either ask this question at each step: is it possible to come from left or top or diagonal? We can check the possibility of whether it was possible to come to this cell from here, here, or here. If we look at this, the gap penalty is not 10. Okay, in order to have 2 here, to be able to come from the left cell, the gap penalty must be +10. It's like gap reward. Okay, we don't have a gap reward, so it's not possible. This 2 is not. We didn't get this number 2 from left. And similarly, gap penalty. If the gap penalty was 0, we could have come from the top, but gap penalty is -8, so this is also not possible. So the only way we could have come from is from this diagonal. And also -6, -4. We could have taken this path if the alignment of A with an E was 2, but it's not 2, so this was the way. So we can either ask this question at every step of the traceback, or what we can do is we already know where we came from actually when we are filling in the table, right? I mean, when you fill the table, you know when you're writing that number in the table, you know which one you choose from. Okay, you choose a number, and you can keep up a second table which just stores your options as an auxiliary data storage. You can have a traceback table which just stores which option you choose. Is it top, diagonal, or left? Okay, you can use 3 characters in that table just to show you at each cell where you came from to that cell. You can keep this separate table, which is going to save you time when you are doing the traceback. Okay, if you want to save time during traceback, you can fill in this additional table during the alignment. And you can align your sequences, and you can do your different examples by using an applet in a Canada website. Let's see if it's still up, this website. It may be outdated. Let's see, but you can find many examples similar to that. I mean, sequence alignment is a very well-studied problem. You can find many applets, many applications that do sequence alignments. Yeah, just somehow, are we connected to the internet? Let's see. Our internet connection may be down. Yeah, there's some problem with our internet, no internet access, so, but you can try this link. Even if this link is not functioning, you can find other applets on the web. Now, there are variations of this global alignment. Sometimes when we are comparing sequences of very different lengths, for example, if you're looking for a single gene, a human gene, for example, we know the sequence of a human gene, and we are looking for this human gene in the mouse genome, okay? And when you're aligning such a short sequence with a very long sequence, it will be impossible to get a good score, okay? If you're going to penalize every gap, one of your sequences is of length, for example, 1,000, the other is of length 1 million, okay? You are going to need about 1 million gaps to have a global alignment. That doesn't make sense. This global alignment, which penalizes everything, every gap, is not very convenient to do such alignments if you want to align two sequences with different lengths. So one variation of the global alignment is called semi-global alignment, which does not penalize terminal gaps. So if we have a gap at the ends of either of these sequences, we do not give any penalty. We just ignore them, 0. And so when we are comparing the score of this, we do not incur this gap penalties, and the score becomes something positive. So this motif TCT occurs exactly in the larger sequence, so it should have a good score. This is how you can find them. And if you use global alignment, you couldn't even have found this TCT there. Because to optimize globally, these local matches may be ignored. Okay? And because the goal of the original global alignment to optimize the alignment globally. So we may make some non-optimal choices to have this global alignment. So if you're looking for a small motif match, you may even not be able to find it at all. Okay? Not forget about having a bad score, you cannot even maybe find it. Okay? So because your goal is to find a match globally. Yeah, I mean, in other words, for example, imagine we have a T here, okay? We have a C here, and we have another T here, okay? In addition to this TCT in the middle, in addition to that, imagine we have a T here with a lot of other A's, for example, a C here, and then a lot of A's, and a T at the end, okay? If we had used linear gap penalty, the score of having this, matching this T, okay, matching this first T with the T here, and matching the C with the C here, and matching the T with the T at the end, would actually exactly score the same as this alignment, okay, if we penalize the gaps equally. So we would not, maybe we couldn't find, they would score the same, they would both be optimal. But imagine a very slight situation, a different situation where we have some mismatches. You could not have actually found the small sequence you are looking for. So this variation, semi-global alignment, if we have a shorter sequence, it ignores the gaps at the terminals, at the beginning and ending of these sequences. This is called semi-global alignment. So how do we do it? What do you need to do? How are you going to fill the table to make a semi-global alignment? Okay, how are you going to modify these equations? Let me show you the table. So, how can you make algorithmically? How can you modify your algorithm so that the gaps at the ends of either sequences? Okay, if we have a gap at the end, you don't want to penalize it. So how do we do it? Modifications.
We have at the end, which means that this side and the outside.
Okay. The first thing is actually your first row and first column. They indicate initial gaps, right? The first row indicates initial gaps in this sequence. I mean, if you're going down, taking down this path, means that you are putting gaps to the letters at the beginning of this sequence. So we have gaps at the beginning of this HE, and so we are aligning this with gaps. But we have to consume anything from the first sequence. So if you do not want to penalize them, what do? We do not have these negative numbers at the first column, right? We just put zeros here. The first column, all zeros. The first row, all zeros. It means that if you have a gap, it means that you can start your alignment from even here. You can start your path from here without incurring any penalty. But right now, starting a path here means that, imagine you started a path here. What does it mean? It it means that this HEAG is aligned against a gap, against gaps, and that was the penalty of this minus 32, aligning all three against gaps. But if we have all zeros in the first column and row, it means that we can start the alignment anywhere. Okay, so this one solves part of the problem. If we have a gap in the beginning, we do not penalize it. What about gaps at the ends? How are you going to do that? Just modification of the initialization does not solve the problem completely. We need to solve the end gaps as well. What?
The other two sides of the square. I mean, these two squares stands for the first part, alignment, and the other two sides stands for the end of alignment.
Yes. So, what do we do for those other sides? Initialize them? Any ideas? Yeah, exactly. So we may have, so when you reach either at the last column or the last row, when you reach that column, you may have accumulated some score. Okay? For example, imagine the case, do I have, yeah, all of them are filled. Yeah, let's look at this. Let's look at this one. For example, imagine you are here. Okay? You come from here, you came to this cell. Now, after you come to this cell, it means that you are end of one of the sequences. So, after arriving, as you can see, it's 7, it's not 0. I mean, it has some positive score. If we put just zeros at the ends, that will be wrong. But after we arrive at the bottom row or the rightmost column, going right or going down at these last column, last rows should not be penalized. Okay, that's how we do it. I mean, after you arrive at a cell in the last column, going right. So from going, for example, from 3 to 2. For example, this one, from here to here, as you can see, it's penalized -1. We should, if it was a semi-global alignment, we should not penalize this going down at the end. Okay, so this 3 to 2, 3 should stay the same. So if we have a 3, for example, we would be able to keep the 3 like 3, 3, 3, 3, 3 all the way. And sometimes it may increase. So, but it may not, it shouldn't decrease. This is going down at the last column means that you are putting a gap at the end of one sequence, and going right at the last row again means the same thing, putting a gap at the end of one of those sequences. If you don't want to penalize them, it should be free. You should be free to go to the right without incurring any penalty. So this is how we do the modification for semi-global alignment. Now let's take a break, and we are going to continue with local sequence alignment.